Yo, what is up, people? It is your host, Aphelion, and welcome back to another episode of the Ephemeris podcast. This will be the penultimate episode of season 1. And, yeah, I don't know why I'm unusually excited about the end of season 1 and going into season 2, but it probably has to do with the fact that now that I've looked at some of the topics for what we're going to cover in season 2, that it's going to be an interesting season. There are going to be some. It's going to be out of my comfort zone, I think, because I don't know. The history of science isn't something I've been like, oh wow, fascinated about, and I haven't really looked into it. So I think it'll be fun to go through that phase of just looking at what was discovered and like some cool theories that came out of people studying astronomy and stuff like that. But that's enough about getting excited for season 2. Let's focus on what we've got today. So today's topic is globular clusters, which means that the last episode will be about nebula. And so what we're going to talk about today is we're going to talk about globular clusters, but not just, what they are, more of what they are compared to open clusters, because I want to give a new format to looking at what of this episode, and then we're probably going to get into some cool characteristics as we do that, and then at the end we will look at some helpful parts about detecting these clusters. So let's begin with star clusters in general and what's up with them before we get into anything crazy with comparing star clusters. So star clusters are generally defined to be groups of stars with common origin that are held together by gravitation towards each other. And for the record, let's just be clear, they're not affiliated in any way with galaxies. In fact, they are different because galaxies aren't held together with just the gravity of the objects in it. There's like stuff to do with dark matter and clumps of dark matter. So they're not quite like star clusters where gravity makes up for all of that holding together, I guess. Star clusters tend to form from the same molecular clouds, which explains their star similarities, which I think we'll get into in a moment. But essentially, yeah, because they're from this same molecular cloud, they're going to be similar population of stars, which means they're going to have sort of the same contents. Maybe not necessarily in the same or well, actually, their age will also be similar, so they might be in the same part of stellar evolution too. So, yeah. Another thing, and this will probably be one of the last things, is clusters only form when the gravity of stars formed in that region is strong enough to keep them close to each other. Otherwise, they just kind of disperse into just what usually happens to other star forming regions in space that are probably in galaxies or something like that, or somewhere near them, right? So there are two general forms of clusters, and they're differentiated by age. And so you have globular clusters, which are spheres of ancient stars, which are very closely packed together. And just for the fun of it, I like to label them the old school compared to the other form of clusters that we're going to get into because of the obvious differentiation in age. So open clusters are a looser group of younger stars bounded together, as you would imagine, compared to globular clusters. And if I were to go through the list of characteristics for both of these things, I feel like it would be kind of boring. So let's switch it up a little. Let's do a bit of a face-off. Do a couple rounds of just looking at specific parts of these clusters and seeing who comes out on top. So if we were to imagine this as a game format, which I initially wanted to do, but I thought, it'd be a bit cringe. I'm going to be the ref. Just decide the rounds. We're going to start the scoreboard at 0-0, and yeah, just keep count and see who wins. All right, so first round, let's talk about the structure. Let's put these guys head to head in terms of structure. So briefly, globular clusters are quite perfect in shape because their gravitation tends to be a little stronger as clusters, and they tend to form spheres. And open clusters, on the other hand, because they're less gravitationally bound to each other, they tend to have like an amorphous structure. They tend to be all over the place, no uniform kind of look to it. So in that regard, in structures, we're going to give the point to globular clusters. Just lovely shape, centripetal concentration, quite dense. They have a really, really nice structure. So round 2, let's look at metallicity. Now this is where globular clusters are going to end up on the back foot. They don't have much metal content because from the molecular clouds that they form from way a little earlier in the universe than open clusters, they're not going to have much metal content to work with. It's going to be mainly hydrogen and helium because at the time that the molecular cloud existed, there was less of that actually having been formed by other stars, right? So with open clusters, you're going to have stars that have formed more recently where those kind of elements are going to be more abundant. So they're going to have more metals. So in that case, we're going to give a point to open clusters and say that's 1-1. That's even. Now, another brief round. Round 3, we got abundance and age. This is a bit of a catch-all kind of round, just because I didn't have anywhere else to put it. So let's look at the abundance and age. So globular clusters have more stars than open clusters, right? And this is like a significant difference. They have millions and millions of stars because of how much they're able to fit within them compared to some of the thousands that are in open clusters. So that's a dub for globular clusters in terms of abundance of stars. But then open clusters, they have more of them in the Milky Way than globular clusters. I hope I said open clusters before that, but let me just say that again. Open clusters have more of themselves in the Milky Way than globular clusters. Right. So that's kind of even so far for this round, but then open clusters don't last very long and they're not able to hold on to their stars. So that would indicate that this is leaning more towards the globular cluster side, but then if you bring into consideration the age of globular clusters as well, I mean, there's not much of an argument to be made for that. So you know what? We're going to give round 3 to globular clusters just because open clusters have a bit of a weakness in terms of how well they hold together, as we've talked about a little bit with the structure. So round 4. Now this is a big round. This is where most of the meat and potatoes of star clusters comes in. This is stellar contents. They can be clusters, they can be perfectly shaped, they can be whatever, but what really matters is on the inside. So let's look at that. So open clusters actually are the ones that are going to have the blue stars over globular clusters. Globular clusters don't have O-type stars, B-type stars, A-type stars, and open clusters do. So all right, first blood for open clusters there, but then globular clusters have millisecond pulsars and X-ray binaries, which is pretty cool. I feel like that's something you got to give a little credit to, so it's a bit even now. But then open clusters, even though they have less stars, they have the same luminosity as globular clusters, which kind of makes no sense and means that, I mean, open clusters just doing better in terms of luminosity. So back towards the lean on the open cluster side. But then here's where the overkill kind of happens with globular clusters, which might kill this debate once and for all. Globular clusters have around 2,000 variable stars. They have RR Lyrae, population 2 Cepheids, RV Tauri variables, right? And open clusters can come back a little bit with, oh, well, we got T Tauri variables, some of them, those young boys, and population 1 Cepheids, but globular clusters have way more than that. They've got RV Tauri, or well, we just mentioned RV Tauri variables. They've got U Geminorum stars, and the list goes on from there, and they're not even going to bother going through that whole list. So, yeah, I feel like, to me, that looks like a dub for globular clusters for me. I think it's it could be an even match. I mean, you could say that open clusters win too because they got some solid talking points in there. So if you guys have some opinions, go ahead. I think I'll set up a poll for this episode, kind of get some thoughts on who won for YouTube, get it in the comment section. Tell me what you think about that. Which cluster is the best? If you happen to do some research on your own and find something that I didn't mention, go ahead, throw that in the comment section. I would be happy to hear about that. So, that kind of encapsulates the cool parts about globular clusters, I would say. Kind of a little bit of a twist on some of the characteristics that shows us, oh, okay, those are pretty cool things. So, one last thing to note, though, is that globular clusters, because they have these stars with very similar ages and compositions, they tell us a lot about the stellar evolutions of stars. They're kind of like a look into the past a little bit. You know, we talked about that with quasars, I think, and how, because they're on the edges of the universe and the light takes a lot of time to get to us, they tell us a lot about what could be for galaxies. Well, here, globular clusters is kind of serving that purpose for stars, because I feel like we probably wouldn't be able to categorize stars based on populations if we didn't know what stars looked like in the past, and kind of why there's a differentiation in metallic content and all that. So globular clusters are helpful in that regard. Again, gives us insight into what stars earlier on in the universe looked like. And I found this nice quote on Britannica, and I apologize for the horrible citation, but I'm just going to mention that quote right here. They say, quote, they are too massive, so globular clusters are too massive to be disrupted by the tidal forces of the galaxy, though their limiting dimensions are set by these forces when they most closely approach the galactic center. So basically what this quote is telling us is that globular clusters are quite undisturbed in the retrospect of the cosmos, so they're really nice to study. And the position of open and globular clusters tells us that there may have been an uneven distribution of mass in the early universe, leading stars closer to the center of the galaxy to evolve more than the ones on the outside, because your globular clusters tend to be on the outside of a galaxy, and the open clusters tend to be closer to the center. So because we see differences in these two, we might be able to say, hey, wait, did the mass get evenly distributed when these galaxies formed? That would kind of lead to similarities, or was it more of a, it wasn't even, and there's differences between these star clusters, and they made different stars. So the merging of galaxies, when you throw that into the mix of why there might be differences, it makes the hypothesis difficult. That's not too significant, but it does show the complexity of evolutions of galaxies. So just, again, another little thing to note. And yeah, I think it was short and brief, but I genuinely did want to investigate a little bit into globular clusters because I thought they were cool. And that is pretty much all I have for the content of globular clusters, and therefore the content of these episodes. And yeah, I hope you guys have enjoyed listening to the podcast episode today. If you did, make sure to leave a follow on Spotify if you're listening on Spotify, and I would genuinely appreciate a follow on YouTube if you are listening there. But yeah, until next time, when we will talk about Nebula in the last episode of Season 1, I will see you guys later. Peace.